Hello, and welcome to Exploring Axon, a podcast where we discuss Axon and its ecosystem. I am your host and Axonic developer advocate, Sarah Torrey. Today I will be talking about aggregates with Allard Buijze. I hope you enjoyed this talk, and let's have a listen. Hi, Allard, how are you?
Hi, Sarah. I'm good. Thank you. How are you doing?
I'm doing great. Thank you again for joining me to talk all about aggregates. So before we start diving into the details of an aggregate, let's talk briefly about where do they fit in within the grand scheme of designing an application.
Yeah. So typically, aggregates are a DDD concept, and when we look at CQRS-based applications, they particularly have a big role in the command model. So the idea of CQRS is that you split the application into roughly two parts, one for commands and one part for queries. And aggregates are an extremely important building block in that command side of the application.
Right.
That's where you'll find most, if not even all, of your aggregates residing. Although the strict definition of aggregates will also give it a place in projections, but it's not as dominant. So typically, when
Mm-hmm.
we talk about aggregates in the context of DDD, in the context of CQRS,
Yeah.
then we typically mean the command handling side of an application.
Gotcha. And so at a later time, I will talk about event storming and event modeling and all of those wonderful concepts. But you mentioned command model. Can you go a little bit deeper on that?
Yeah, so the command model is basically the structure of, let's say, information and logic inside an
Mhm.
application that is designed to, as efficiently as possible, uh, take in any instructions from, for example, users, or they could be external systems, but
Mhm.
instructions for your applications to process. So
Right.
a user clicks a button, for example, and he was given some information on a screen and has to choose and has to submit some other information based on that, has to take an action. So basically, that user will instruct the system to take an action.
Mhm.
Now the system needs to make decisions on that action. Decide, okay, are you allowed to do that? Is this an appropriate time and state of a system to actually do that? Right? Did something
Right.
else prevent this from happening? Or and if everything is allowed, it should decide, okay, then what is the result of this action? The
Mhm.
result could be that your loan application has been approved, or
Right.
a money transfer has been initiated, or
Mhm.
there something happened, and typically in CQRS in the CQRS context, the aggregates will emit these events. So as you
Right.
noticed, I said, well, a loan application was approved. Well, that's an
Mhm.
event, right? Something happened,
Yeah.
and typically they will emit those events to notify other components that this actually happened.
Sure.
And meanwhile, the state of that model has changed
Mhm.
because you cannot approve a loan application again, or maybe you cannot reject it anymore. You cannot modify it anymore. So every
Mhm.
action that's there has influence on the next action, on the next possible outcome of these commands. And
Mhm.
that's what you design the model for. So basically, you're not trying to solve all of the problems of your application in just random places, but you
Right.
organize logic into components,
Mhm.
where an aggregate is one of the possible types of components that you can use, and
Right.
it's the most important one in that command model.
I see. Yeah, that makes sense. And you mentioned the definition of an aggregate. So, generally speaking, just in English language, the definition for an aggregate would be a whole that's formed by several separate elements. In domain driven design, more or less the same thing. I do want to sort of go into the definition that Eric Evans gives in the Blue Book because uh, it's a really good definition, but not all of the points are super clear. So can we sort of go through that definition a little bit?
Yeah, yeah. So the definition in the blue book definitely goes a bit deeper than just let's say it's as you said, it's a whole formed by individual elements, because in the end that's what it is, right? Is an
Right.
aggregate is there's a group of individual component that acts as a whole, um, especially with regards to data changes, right?
Yeah.
So that means that from the outside, we cannot, even though there's multiple components that all take individual actions and have individual modifications, from the outside, we cannot see that. From the outside, we
Right.
will never see that an aggregate is actually composed of these multiple elements that
Hmm.
each take a small part in whatever we call a change, right?
Right.
So when we approve a loan, or I don't know why I came up with that example, but then probably that approval process is not will have influence on different parts of that model, right? There's different
Hmm.
parts within that aggregate that need to be modified, which together we call approved. We never
Right.
see a loan as half approved.
Sure.
Yeah, we approved the first part of your loan, but not the second part. Well, that doesn't
Right.
happen, right?
Yeah.
If you have a loan that consists of multiple parts, it's either fully
Hmm.
approved or it's fully rejected.
Exactly.
So that's one aspect of it. So from the outside, we cannot observe, let's say, the state halfway, right?
Hmm.
That's
Yeah.
one aspect. So that's the one unit. Then the definition also talks about an aggregate root and holding
Hmm.
references to an aggregate. And
Right.
this is when you look at how to implement an aggregate. Well, we are stuck, quote unquote, with object-oriented programming, right? So we need
Exactly. Right.
classes and we need instances of those classes.
Hmm.
Um, so we need one of these classes to represent the aggregate as a whole to the outside world, and make sure that whatever decisions we make on the inside and whatever information we show to the outside is always safe, right? So we
Right.
need one class that takes that prime responsibility, and
Hmm.
that's the one we call the root. And the
Right.
reason why you're only allowed to connect to that root is anything else than the aggregate root. So that one class that we've defined as the gatekeeper of state.
Hmm. Right.
Anything else can change, right?
Yeah.
Anything else that root object can decide to remove a part of that loan and replace it by another
Hmm.
object. If we had a reference to that part of the loan, it would be now an invalid reference, right? It's like
Exactly.
if you remember your car by the actual wheel that's on it, well, don't
Yeah.
change your tires, right? Because you'll lose your car. Well, that's
Hmm.
not
Not gonna make sense. Yeah.
so that's important to keep that reference. And
Hmm.
reference is somewhat an abstract term here. It means when you have an identifier for your aggregate, it's the
Hmm.
aggregate root that is given. It's that identifier, but it also
Yeah.
means class references, object references, if you have an object-oriented language. Um, so so that aggregate root is a very important has an important role, and it's
Hmm.
typically just there's always, when you look at an aggregate, there's always one object there that has the same name as the aggregate root. So if you look at
Right.
order and order lines, we talk about an
Hmm.
order.
Yep.
So there's a class order, there's a class order line, but we call the whole thing an order.
Hmm.
And that is already a hint that the order class, that is our aggregate root.
Sure. Sure. That makes
So
sense.
that very often the root and the aggregate have the same name, and that might make it confusing sometimes. But if you just
Hmm.
realize that when we open a little Pandora's box and we see the individual elements, then we
Right.
know it's a root and there's entities, and otherwise it's just the whole box. It's just the aggregates.
And I'm actually glad that you brought that up because within that definition that we just talked about, he mentions that the aggregate is the cluster of entities and value objects, and it's defined by a boundary, right, that comes around it. So um, we, you talked a little bit about the aggregate root, and it has an identifier. And that's why we say that aggregate root has to be an entity as opposed to a value object. Can you define value object and entity also, just in case some of
Yeah.
the listeners may not know that?
The main difference is that entities have a conceptual identity,
Hmm.
and their attributes, the attributes of that entity, don't define the entity, but they describe the current state, and that state
Right.
might evolve But while it evolves, we still recognize that entity as the same thing.
Mm-hmm.
Right. So in human interaction, you can change attributes. You can wear a hat. You can start wearing a scarf in the middle of summer. But it will still be you, right? Because
Sure.
in human interaction, it's not the attributes that make the person. It's the
Mm-hmm.
identity that makes the person. And without
Right.
becoming too philosophical here, but and it's the same in programming with entities. So an entity can change attributes, and it will still be recognized as the same,
Mm-hmm.
and vice versa. You can also have two entities that have the same attributes, but we
Mm-hmm.
still consider them different instances. They're still different ones, right? They
Mm-hmm.
just happen to be similar right now, but they may evolve in a different way. That's why
Mm-hmm.
we see them as two different things. So
Mm-hmm.
they are stateful, if you will.
Yep.
Now, when it comes to value objects do not have a conceptual identity. They are just they're immutable, and they have attributes, and the attributes define the value object. There's nothing else.
Right. Mm-hmm.
So, again, in human interaction or in daily life,
Right.
money is a value object, right?
Mm-hmm.
It has an attribute, which is a currency and a valuation,
Right.
and or denomination, and that's it. That's the value. And if we have a bill of 10 euros and another bill of 10 euros, then we have two the same bills, and we can swap them around, and nobody cares. You can then
Right.
go to somebody and say, here's a 10 euro bill, and he gives you two 5 euro bills. It's
Mm-hmm.
the same. There's no you don't feel like you've lost your bill, right? There's
Yeah.
no conceptual identity to that bill anymore. It's just the value of the thing. And that is a
Mm-hmm.
very powerful concept, because in math, basically everything is a value object, and it allows
Yeah.
you to do a lot of interesting mathematical aspects. So they
Sure.
both have their pros, but in aggregates, since aggregates are about change of data, it means
Mm-hmm.
that the aggregate root must always be an entity, but then
Mm-hmm.
within the aggregate boundaries, we can have certain value objects, because
Gotcha.
it allows us to do mathematical computations more easily. We all know
Mm-hmm.
from the different discussions that you have immutable state is a very powerful concept,
Yeah.
especially when it comes to managing complexity of mathematical type operations.
Right. And so that's great. There is another part of the set definition in the blue book that I was not quite sure about, that I wanted to sort of read through it and maybe dissect it a little bit more. He also mentions that we have to, within the aggregate, define properties and invariance as a whole and give enforcement responsibility to the root or some designated framework mechanism. So how would you go about that?
Yeah.
Let's talk
So
a little bit more about
what does that
that.
mean? Um,
Yeah.
so the invariance that he speaks about is mainly that the consistency boundary. When I started talking about aggregates, I said
Hmm.
there's a couple of changes that may occur within an aggregate, but from the outside we cannot see them.
Right.
That's where he's talking about. So even though there's so let's talk about a loan application. Let's say we're applying for a loan, and that
Hmm.
loan consists of three parts, right?
Right.
There's a bit of mortgage and a bit of this, bit of that, and you want the whole application to be treated as a single thing, right? That
Right.
let's assume that's important.
Exactly.
Now, when we approve a loan, that probably means we need to approve every single item under that
Item.
loan, right?
Sure.
But from the outside, we don't see that, so we will never be able to observe a situation from the
Hmm.
outside where a loan was approved, but one of the individual items in the loan was not.
Hmm.
And of course, if we just build plain objects and don't have any consistency boundaries or one of these mechanisms that the definition talks about, then we can see that, right? There's
Yeah.
a
Yeah.
possibility where we can observe this group of objects in this halfway state.
Hmm.
So we need the root to enforce that, and basically it enforces that. Oh yeah, doing this operation implies those operations over there,
Yeah.
um, but still that will not prevent that mechanism from or that state from being visible. So
Hmm.
probably you need some framework mechanisms such as locking, right? Making sure
Right.
that a call is blocked while reading, or we keep a mechanism where we say, well, when you read, you still see the old version because we are in the process of building the new version of that state. So there's
Right.
different ways to design around that, and they well, typically one of the things Axon, for example, does is when you try to access an aggregate concurrently, well,
Yeah.
conceptually you cannot do that. Conceptually, it has to be one invocation after the other because otherwise you can observe this halfway state.
Right.
So we use we use different mechanisms, but one of them is locking. Right, one of the options that you have is locking, and we just say one execution will go after the other, so that we will never execute on a halfway state. We'll always either execute on the start state or at the end state, but nothing nowhere in between.
Yeah.
And that's really important. So there's basically rules in an aggregate that says there's a number of transitions you can have. And even though a single transition might internally consist of a number of steps, we will never ever observe those midway steps.
Those little
And
steps, exactly.
that's the invariance, essentially.
Makes sense. Yeah, very good. So we are talking about some examples of aggregates, and you mentioned the example of a loan or maybe a car. There was an actual example that we talked about, or he talks about rather in the blue book, that was the example of a car. And you actually touched on a little bit with the wheels. You know, if you change the wheels of the car, it's still within the boundary of the car. So that car can be your aggregate. Um, and then we kind of talk a little bit about another aspect of another aggregate that you can actually take out of the car, like an engine, because an engine itself can be an aggregate because you care about the that specific engine. For instance, in a car, if you need to repair the engine or the change the engine, the identifier of the engine is important. Therefore, the engine can actually be an aggregate outside of the car aggregate. So those I thought were really interesting examples of aggregates, because depending on, again, we could go back to that notion of what kind of problem we're trying to solve. The aggregate can change, and you can make it broader, looking at a higher level, or you can make it a little bit more detailed, looking at a little bit more specific, depending on what we're trying to achieve. You had an example a while ago, we talked about it, and that was the example of a ticket sale at a movie theater. Can you talk about that a little bit? Because that was really interesting to me, because it helped me look at an aggregate in a little bit a different way.
Yeah. So there, it started with a challenge that a company once set out, and they allowed people to submit solutions to that challenge. We didn't manage to get it done within the deadline because we had other priorities, but still we discussed our solution with the people from that company. And basically, the challenge they had is, imagine you need to sell tickets to a large, actually, it was a very large event that they typically do in stadiums, right? It could be a football match, it could be, I mean, sometimes there's music shows in those theaters. So we're talking about thousands of tickets, right? And they are usually sold out within seconds, right? If you just
Right.
have a popular rock band come
Yeah.
over, then the biggest arena is sold out in a matter of seconds. So how do you keep consistent? I mean, eventually every ticket represents a seat, an
Right.
actual physical seat. And if you buy
Exactly.
5 tickets, you don't want to be scattered around with your friends, right? You're scattered around the stadium. No, you
Throughout the
want to be
stadium. Yeah, exactly.
exactly.
Yeah.
So you can wave at each other from opposite sides. No,
Text.
you want to sit
Exactly.
next to each other, right?
Yeah.
But then there's depending on the type of show, there's challenges that, yeah, but if two parents come with two kids, you want to sit next to the kids, but the kids pay a different rate than the parents.
Exactly. Right.
So there's different areas. So what they one thing that you always need to do is you need to break the problem down, right, into smaller pieces,
Sure.
because the aggregate is, as we said before, is a consistency boundary. But if you make that boundary too big, it basically means your performance will grind to a halt, right? So you want to
Right.
break that down. And what they did is they had blocks of seats, and if you look at a stadium, then obviously certain areas are, or any movie theater, certain
Yeah.
areas are more popular than others, right? So you'll have different price ranges for different areas. Um,
And
But
of course, we
still,
can't nest aggregates, can we? We can't have aggregate within an aggregate.
no, you cannot have it because
Sure.
you cannot have two consistency boundaries. Either it's
Exactly.
consistent or it's not. So
Or it's not.
if you
Exactly.
start nesting them, then either you have a big problem because, well, if we look at the definition again, you can only hold references to the roots. So they
Hmm.
can't be
Right.
nested because there's only
Exactly.
then the top one is the root. So
Right.
we're just faking ourselves into believing we've got many, but
Exactly.
then we just have the worst of all options. Um, so the when they broke it down, they said, okay, we'll just design areas, or they call
Hmm.
it blocks, right? You have
Yeah.
certain blocks, and then you buy a ticket within that block, and then you're assigned a seat within that block. Because in the
Hmm.
end, you don't care whether you're in seat 1A or 1B or 2A or 2F, or right. It's just a few meters apart, as long as you're not behind
I was gonna
whatever
say,
all the way behind. But those that would be
yeah.
a different block.
Or
Um,
unless you're short like me and you just get stuck behind somebody
well,
who's
then you
tall.
just have to buy block one. Is row one is what you need. Um,
Right.
um, and depending on the show, you definitely don't want to be on the first row.
Right.
Um, so they design it in blocks, and then you basically buy a ticket within the block. And of course,
Hmm.
then you don't have concurrency. You just have, well, a lot of requests coming in for tickets in that block, but you treat them one by one, quote unquote, to make sure that you can fill that efficiently. But you'll
Hmm.
still have massive concurrency when it comes to the theater as a whole, because you'll have
Hmm.
different blocks, and they can make their decisions in an isolated way.
Hmm.
So basically, you'll have blocks of, let's say, 100 seats or 1,000 seats, depending on how large the
The
stadium is,
venues. Yeah. Hmm.
the venue is, and that way you can make sure that you have a consistent rule of, okay, when you buy 4 tickets, we will assign the 4 adjacent seats in the same block, and then we'll know exactly which seats are available, and you can have little
Hmm.
algorithms for that to decide how you want to make sure that the children will always sit with their parents and not next to some random people on their own,
Stranger.
right?
Right.
Random stranger.
Exactly.
So yeah, so that was an interesting scenario, and
Hmm.
and it shows that we need, when it comes to designing aggregates, we need to think about the interaction. So what is
Hmm.
this consistency that we want, right?
Right.
What is the behavior we expect? And
Right.
in this case, the behavior is, well, we want, when we sell 5 tickets, we want those 5 people to sit together,
Hmm.
right? That's the behavior, and it's not because a seat is a, well, we need the seats to be sold. It doesn't mean the seat is the aggregate,
Yeah.
and it doesn't mean the stadium is the aggregate, because we need to make sure that everybody gets in. So that
Hmm.
we need to look at these rules, and what it's more about the changes. What are the invariants, right? What is it that we want? What is it
Exactly.
we never want happening? Well, we never want
Hmm.
a kid to be away from his
Away
parent
from the parents. Yeah. Hmm.
in that scenario, and that's what drives the design of an aggregate much more than the. I always say we have this tendency to look at nouns, and then say, oh yeah, we have a seat and a block and a stadium, right? So those
Hmm.
are
Yeah.
our entities, and those are our aggregates, because then
Right.
we can guarantee that we sell a seat exactly once, right? But that's not the invariant when we look at the real story, and when we look at the
Exactly.
changes. And then the seat is not even important when
Hmm.
selling seats. It's not, the actual seat is not even important. It's more about the structure of the block, and then as a result, when you sell 5 tickets, well, then they are those 5 seats as a result, because that's basically what our consistency rules have dictated.
And I think what you said, the word behavior, I think is important here because we're looking at the business question. Basically, we're looking at what is it that we're trying to achieve with this particular aggregate. Are we trying to make sure that people who are buying tickets together as a family can sit together, or are we just interested in selling this particular section of the stadium, for instance? So again, kind of goes back to that main question of what is it that we're trying to, what you mentioned something to me a while ago, which was like the verby nouns, right? We're trying
Yeah.
to
Yeah, so
to kind
aggregates
of,
are very often nouns, right? So
yeah.
the block, or, well, block
Hmm.
is not a good example in this case, but the best aggregates are verby words, right? So they're not actual verbs because they're nouns, but there's this concept of a process in this word.
Hmm.
So an application, right, is to apply for something, and
Right.
the benefit of those aggregates is they, in their name already, they carry a process, and a
Hmm.
process has a start and an end. And it's nice
Right.
for aggregates to also have a life cycle where they work towards a goal. And that's if that goal has a clear end, then that's always better
Right.
in the design of a process. Of course, in the example I gave earlier with the stadium, you have a block. Well, they happen to call that a block, but it's about
Yeah.
the selling the block, right? So the
Sure.
process is to sell. So while I'm always looking for verby words, uh,
Hmm.
you will not always find them, and it's not a bad
Right.
thing per definition, as long as you find the process
Hmm.
inside of what an aggregate does.
What an egg. Yeah, exactly. Makes sense. Um, Now let's talk about aggregates and event sourcing. How do aggregates relate to event sourcing?
Yeah, so that's actually a very important one, because there's a lot of misconceptions around event sourcing. And
Right.
so event sourcing is not about having events go from A to B, right, from one
Hmm.
location to another. Event sourcing
Right.
is essentially a way of storing the state of an aggregate. So
Mm, okay.
instead of saying, okay, we have an aggregate and it is um, well, it could be the block in the stadium, right? And let's say,
Hmm.
okay, we've got 10 seats to sell in that block, and we've
Hmm.
sold seats 1 through 5. That's
Right.
possible. So we can keep that as state. We can have 10, let's say, little flags, and we can
Hmm.
switch them on and off as these seats get sold.
Right.
Um, but then there could be a sale in progress, right? There could
Hmm.
be somebody claimed the seats, and now they have 15 minutes to actually pay for them, because paying is still an asynchronous process.
Right.
So that needs to be, the payment needs to be confirmed within a certain amount of time. Otherwise, the seats are released again, and then
Hmm.
anybody can claim them, right? So it's more complex than just having 5 flags. So now we're sorry, 10 flags. Now we don't have 10 flags anymore. Now we have 10 different options. Like, okay, this seat is reserved, but is reserved for the same transaction as the seat next to it. So that
Hmm.
state gets complex, right?
Right.
And every time we overwrite it, we lose the previous state. We lose the fact, why is seat number 2 available while 1 and 3 are taken?
Sure.
Um, well, probably the history of what happened
Hmm.
can tell us that, but if we don't
Right.
store that, then we don't have that information anymore. We just know the
Hmm.
current state. So the thing about event sourcing is, while we are emitting events typically in these systems to explain what
Hmm.
happened,
Right.
why not use those events to recalculate, use those events as our only source of truth?
Hmm.
So when we say we want to sell seat number 2, what we do conceptually is look at, okay, what is the state of that seat, and we look at the
Hmm.
past and say, it was cancelled, or that's the, so yes, we can claim it, right?
Hmm.
Or no, it's been claimed, and the rule says you cannot claim a seat more than once. Obviously,
Right.
that's
Yeah.
that's a rule. So we can use that. And so event sourcing basically allows you to recalculate the current state of an aggregate using
Hmm.
the history of that aggregate. And that sounds like complexity, and why would you ever want to do that? Um, and that comes down to the quality of the event stream that we produce. If
I
we
see.
if we were to say we store states and we generate
Hmm.
events as a side effect, then we cannot fully guarantee the correctness of the event stream. There might
Right.
be a situation where we forgot to emit an event, or we emit an
Mm.
event that we did not replicate correctly in our state, and then we make decisions. We make decisions on another um, source of data that we're actually
Right.
emitting. So we don't have a
Hmm.
single source of truth anymore, right? Our
Gotcha.
event stream is definitely not the truth; it's derived
Yeah.
from the truth now.
Yeah.
And with event sourcing, you basically turn that around and say, no, the events are now the truth, and every decision we make, we look at
Hmm.
the events.
Right.
And Axon's goal is to make that as efficient and as easy to use as possible. So any downsides of event sourcing, we want to mitigate those, and make it easy to use event sourcing, because it
Yeah,
guarantees that the stream of events is like your single source of truth. But
exactly.
it is important to realize that the aggregate is your unit of event
Mm-hmm.
sourcing. You
Right.
event source an aggregate, not a
Mm-hmm.
system. It is
Right.
the
So then I'm actually glad that you brought up Axon because I do want to talk about Axon framework and the server because I know that the framework itself has annotation that actually helps with the aggregate. Can you talk a little bit about that, especially about the aggregate root? Because I had the aha moment a little while ago that we were talking about it. So can you go through the annotation a little bit?
Yeah. So in Axon, you will you can mark a certain object as an aggregate root, or you can um, and it may have a number of entities within it, right? Just according
Mm-hmm.
to the definition of DDD, you can have a group of
Right.
entities. One is the roots, and then when you event source an aggregate, what you need to do
Mm-hmm.
is you need to separate the logic into two parts.
Right.
One is the part where you define the logic that when a
Mm-hmm.
command comes in, what are the decisions you need to make? What are the options, right? So
Right.
somebody wants to buy 5 seats. Well, you need to check:
Mm-hmm.
do we have 5 seats all together connected, or are there no children involved? In that case, you might go around the corner and say, okay, we put 1 seat in the row behind them, right? All of these rules we can check them at that point, and then we decide. Then we make decisions, and
Mm-hmm.
we make decisions by applying events.
Right.
Now, when you apply an event, that means that you've made this decision, right? We're assigning seats 1 through 5 to this
Mm-hmm.
group, right? For
Right.
this transaction.
Mm-hmm.
That's the decision you make. But that decision, of course, has influence on the next decision that's coming in. So we need to update some
Exactly.
state somewhere to mark seats 1 through 5 as
Something changed.
yeah,
Right.
something, as they're now booked, right?
Yeah.
They're claimed.
Mm-hmm. Mm-hmm.
Um, and in Axon, you can annotate your some methods with at event sourcing handlers, and those are
Mm-hmm.
the methods that get invoked with past events. So
Yes.
any past decisions, whether it was there's a half a nanosecond ago or whether it was 5 days ago, that doesn't matter. So
Yeah.
it allows you to reconstruct the current state, and Axon will invoke all of these methods using the past history. So you can very quickly recalculate the current state of an aggregate,
Mm-hmm.
and that really helps you because you don't have to reason about the entire history. You can reason
Yeah.
about the current state just now,
Mm-hmm.
but it's been built up of history, and
Right.
that way the history and the decisions you have are always consistent.
Right.
So you will
Exactly.
never see a situation where you've booked seat number 1 twice, and
And then get a lot of angry customers coming at you.
exactly.
Yeah, exactly. There's just one more thing I wanted to talk to you about, going back to the Blue Book. There was one area where he's talking about the aggregate boundaries and the transactions and distributions. So he mentions that within an aggregate boundary, apply consistency rules synchronously, and across boundaries, handle updates asynchronously. Keep an aggregate together on one server and allow different aggregates to be distributed among nodes. Can you tell me a little bit, because you and I talked about Axon Server and how it actually um, works beautifully and magically with the framework to actually get this done. Can you elaborate on that?
Yeah. So if we so let's start with the definition, right? So why would you
Yeah.
want to keep the aggregate in one place? Well, that
Mhm.
comes down to consistency. Consistency in distributed systems is extremely hard, right? There's a CAP
Mhm.
theorem, so you have consistency, availability, and partition tolerance. Well, if you have a distributed system, then you need the partition tolerance.
Right.
So then you have a choice between consistency and availability.
Mhm.
So we want consistency. That means availability is at risk. If something happens, we just become unavailable. Well, we don't want
Right.
that. So an aggregate will run on a single node, so that there's no network partition. We don't need partition tolerance, so we can have the consistency.
Right.
But of course, if that one node where an aggregate runs, what happens if that node goes down or something
Mhm.
happens?
Mhm.
If you have a distributed system, then how do you make sure that the aggregate lives in one place without keeping some administration of which aggregate lives where. And
Exactly.
that's where Axon Server comes in. And Axon Server allows you to consistently route messages. So when you send two commands to the same aggregate, so let's say
Yeah.
two orders come in for the same block, right?
Mm-hmm.
Now, the way you execute the first order, or the first command, the first,
Yeah.
I'm overloading the term order here. The first
First
buy
request.
transaction, the first request,
Right.
will
Exactly.
influence the outcome of the second one. So one thing you
Sure.
definitely don't want is those to be distributed to random different destinations, and
Exactly.
then to have conflicting decisions in these two places.
Mm-hmm.
Now, there's no way to 100% prevent that. So Axon Framework already has mechanisms to detect those conflicting modifications, and it will reject the
Mm-hmm.
second one and have you automatically retry it.
Mm-hmm.
But Axon Server will prevent that from happening because it will know that you're sending two messages for the same block, so we're
Mm-hmm.
routing it to the same machine.
I
And
see.
Axon Server uses a concept of consistent hashing for that,
I see.
meaning that if you have um, two commands with the same destination,
Mm-hmm.
it will use a hashing algorithm to choose a destination based on that value. So there's no ledger to keep track of which
Mm-hmm.
commands to send where. It's a very
Yeah.
simple calculation, and they get routed to the same destination. And that allows Axon Framework to then optimize and say, okay, there's two commands for the same aggregates. We'll load it
Mm-hmm.
once, we'll execute the first command, and then on the result, or on the state that basically the
Yeah.
first command left, we're going to execute the second one. And
I
that
see.
way you have this full consistency. You still have the scalability and the possibility of distribution
Of course.
and all the horizontal scalability that it gives you.
Mm-hmm.
But we still also have the consistent rule, the consistency guarantees that we need on the aggregate level.
I see. Yeah, that makes a lot of sense. Fantastic. That makes it a lot more clear for me in terms of aggregates, because that was one of the big things for me when I first started talking about the aggregate with you, that there were some really unclear points. So thank you for clarifying all of that. Any additional items that you'd like to mention?
Yeah, there's one thing that's really important. So I said an
Yeah.
aggregate is a very important building block in a command model, and I want to stress the fact that it is not the only building block, right? There's
Right.
a model is a command model is typically more than an aggregate, and especially with event sourcing, there's some challenges around. Usually, set validation is one that comes up, right? How do you
Yeah.
guarantee that when we have a couple of aggregates, how can we guarantee a certain set of information is consistent across these aggregates?
Mm-hmm.
Um, and that cannot be solved within an aggregate by definition because you're going
Mm-hmm.
across boundaries. So we need different elements, and I will not go too much into depth about those, but there's definitely more than just aggregates to design with. There's a whole, the book by Evans describes a number of building blocks you can use. And simply
Exactly.
because you're doing CQRS doesn't mean you only need aggregates. There's these other
Exactly.
blocks, they're really
There's
useful.
a lot more going on. Yeah.
There's a lot of different shapes of bricks in Lego,
Elements.
and
Exactly.
we all need them, right? You don't just need the square ones. You'll need
Don't
different,
worry, I'll go
different
into them
shapes
and
as well.
dissect each one of them. So
All right,
I will
sounds
come
good.
back to you on that. Now, just to kind of, I have an additional question. Within an application, going back to aggregates, of course, there are a number of things involved outside of an aggregate. Are there any limits of how many aggregates you could have in an application? Does that make any difference? I mean,
No,
of course,
there's
you don't
yeah.
want to have like a million of them, maybe. I don't know, maybe you do.
It's well, the thing I always look at is not so much the number, no, or not just the number of them, but I look at typically how active are they, um, uh, how much interaction is there on aggregates, and do they really need to be?
Mhm.
I'm looking for these boundaries, right? You want to explore. You definitely don't want one aggregate, right? The
Right.
one system aggregate is something we jokingly use when somebody says, "I want full consistency in my system." Well, that's great. You'll have one
All in
aggregate.
one.
That's it's
Yeah.
called system. That's not doable. But you definitely don't want to go the other way either and say, okay, every little aspect is my aggregate, because then there's a lot of coordination between components, and you might just have too much eventual consistency.
Sure.
So you want to find the balance, and there's a number of heuristics that you can use to find that balance. The most important one is obviously these expectations around invariance. So things that you will always want to be true, things you do not want to be able to observe from the outside. But then there's also hints like what is the concurrency on an aggregate. So one example briefly is I've worked on a gaming platform, and you had the concept of a tournament and then individual games within that tournament. Now a game was played by 4 people, and it would last for 10 minutes, and there's a lot of activity within that game with 4 people. But a tournament is 10,000 people. So you'll have 2,500 games concurrently. Now, if you would say an aggregate is the tournament is an aggregate, and then we have games as entities within that aggregate, it means you'll have 10,000 people being very active on a single tournament.
Exactly.
Right? Keeping that
On a single
consistency
aggregate,
is going to be a challenge to make that performance, right?
Exactly.
So what we did instead is say, well, on the tournament, there's not much interaction, right? There's somebody joins the tournament, and there's a few rounds going on, right? There's a bit of calculation who plays which games, and then we have the game as a separate aggregate because it is short-lived, but it's also very interactive, but with only 4 people each. So we can spread that, and we can have much better performance characteristics in our system. And there is no strong consistency requirement between the game and the tournament, except for the outcome of a game, right? But nothing in the middle. And those are important aspects to look at when you design. And that is a very important indicator as well of how many you end up with in the end.
Exactly, and that comes back into the modeling aspect of it, right? When you model,
Absolutely.
you have to just be conscious about these decisions. And just really briefly, I know I keep having questions come up. You mentioned how active an aggregate is. When an aggregate becomes inactive or irrelevant, how do you get rid of it? Do you get rid of it?
Yeah, so with event sourcing, there's actually no difference, because it just means no events happen anymore, and the past is still the past. If you do state storage, then you'll have the everlasting discussions on, do you delete it or do you flag it as deleted? A lot of people say delete doesn't exist, right? But you cannot, because delete
You can
basically
delete the past.
erases all history, right? It's
Exactly.
gone. And with event sourcing, it's not even an option. But with state storage, well, you can just delete an order and pretend it never existed, which is probably not what you want.
So in that case, you just leave it be, basically.
Yeah, you can leave it be, except that if you do use state storage, you're probably storing that in a relational database, and if you use a relational database, then they slow down as you insert more data.
Exactly.
So even with state stored aggregates, you might find yourself just cleaning up because of the need to keep things fast. And with event sourcing, we mitigated that problem in Axon Server, designing for larger numbers of events without slowing down. So with event sourcing, you don't really have the concept of delete. You can make an aggregate. You can get an aggregate into a state where it will reject any change from then on. Right. So if a customer or if a shipment was delivered and over with, well, there's nothing else you can do on that shipment, right? It's just over, it's delivered, it's final, nothing happens. And that's about it. It's never deleted. So in that case, delete doesn't even exist. Yeah.
And what do you do if you don't want anyone from the outside to have access to that aggregate root? So you want an aggregate, for instance, to quote unquote be inactive or not usable per se.
Yeah, so in the framework, we do have a flag that allows you to mark an aggregate as deleted, even when event sourcing. In that case, it will still exist. So as a operations or support engineer or whatever, you will still have access to the data. It's still there. But as soon as the system tries to interact with it, Axon will pretend it doesn't exist. It will just say, "Hey, the aggregate is well, actually, the repository will normally throw a not found, but we have a more specialized exception that says it has been deleted, which is the same as
Okay.
not found, but we just
Right.
give you more information. Like we did find it, but we're not supposed to
But
tell
you
you.
can't access it. Yeah.
You cannot
Yeah.
do
Yeah.
anything with it.
Basically, you can't touch it.
No
Right.
touching. And
No
the nice
touching.
thing is, if you ever decide to, oh yeah, but that event isn't as final as we thought, the only
Mhm.
thing you need to do is change the logic of what these events mean to the aggregate and say, well, that doesn't mean it ended, and you can move the end logic somewhere else, and then from then on you can load it in the aggregate.
Okay.
So that's a way to actually undelete it, right?
And reuse it again,
Exactly.
or at least reuse parts of it.
Yeah.
Whatever you need. Yeah. Ah, that makes a lot of sense. Okay, fantastic. Um, Before I come up with another question, I think that's a good
We could
place to
go
wrap
on
it
for
up.
hours, I guess. Yeah.
I know, right? I know. This was really, really great information. I really appreciate it. Thank you so much, Allard.
You're
And
welcome.
we'll come
Thanks
back
for
with more
having me.
questions at another time. Yeah, for
All
sure.
right.
Have a
Sounds
great
good.
rest of the day.
Bye.
Thanks.
Bye.
Bye. Thank you so much for listening, and I hope you enjoyed this talk with Allard. Please join me next time as I discover more about event handling and query handling. Until then, have a great time and happy coding.